For the next couple of objectives, learning objectives, we're just going to focus on the chemistry of carbon. So we got to answer a couple of questions. Why is carbon so important in the molecules that make up living organisms? That is to say, what makes carbon such a great element for building things like living organisms? And follow up to that, how are functional groups, which we'll define, important in chemical reactions? And you should be able to diagram these five functional groups: hydroxyl, carbonyl or carbonyl, carboxyl, amino, and phosphate. Okay, so here's a little carbon humor for you. Um, you may know that coal is made up of carbon. Diamonds are a special, what's called an allotrope of carbon, or a form of carbon, pure carbon, that's different from coal, which is also pretty much pure carbon. And that diamonds are formed from extreme pressure, usually over prolonged periods of time, but they can also be created almost instantaneously by something like a meteor impact. So, is carbon important in the human body? The answer is yes. It's important in the bodies of all life as we know it. Um, this slide you saw earlier in the chapter, and we just spent a while talking about water. And so most of that oxygen, that 65% of your body mass that is oxygen, a huge chunk of that is in the form of water. And hydrogen is only 9.5%, but hydrogen is much, much less massive, much, much lighter than oxygen. And then you can see close to 20% of your body mass is carbon. And so it's absolutely very important to the bodies of living organisms, and you're going to see why. So living organisms are mostly made up of carbon-based compounds when they're not water. And one of the reasons for that is that carbon is kind of like the Lego of the periodic table. It is very good at forming large molecules. You can mix and match the bonds in carbon atoms in just a myriad of different ways. And as we're going to see in the last part of this chapter, protein, DNA, carbohydrates, lipids, all made up of carbon compounds with a few other elements thrown in. And we'll discuss that in some detail. So, carbon chemistry is so interesting that there is a special branch of chemistry dedicated just to the chemistry of carbon compounds, and it's called organic chemistry. Organic chemistry is a bit different from like if you get organic food at the grocery store. That's referring to organic in a different way. Both of the organic chemistry and organic agriculture essentially refer to the life that is in the substances that they represent. So in the case of organic chemistry, carbon is really the main element of living organisms. And for organic agriculture, it's all about promoting life and not using synthetic pesticides and herbicides and things like that to produce crops. But apart from that, organic chemistry and organic agriculture don't have a whole lot in common. If you were a science major, if you were interested in going into chemistry or into medicine or a number of fields, you would have to spend a whole year studying organic chemistry, and that would just be the beginning of it. So organic chemistry is a study of carbon-containing compounds. Organic compounds range from just a couple of carbon atoms with maybe something else attached to them to millions, billions of atoms all in a row. And most organic compounds are going to contain hydrogen in addition to carbon atoms. So let's get at this question of why is carbon, this concept number has nothing to do with our book, it's from the other course that I teach, but similar material. Carbon atoms can form diverse molecules by bonding to 4 other atoms. Now that's the thing that makes carbon like Lego, is it can form up to 4 other bonds, or it'll form 4 bonds with up to 4 other atoms. And that has to do with the electron configuration. Remember, all atoms want to have a stable valence shell, a completely full valence shell, and however many electrons are present determines how many bonds an atom can form. So carbon can form 4. The reason being that carbon is element number 6, so it's got 4 valence electrons. It's got 2 in the inner 1s orbital, it's so called, which means in order to fill its valence shell, it needs to share electrons with 4 other atoms, form 4 covalent bonds. And really, you don't get atoms that form a lot more bonds than 4. That's kind of the max, because once you get past having 4 valence electrons, if you have 5 valence electrons, that means maybe you'll form 3 bonds. If you have 3 valence electrons, you'll probably get rid of those 3 electrons because it's a lot more stable than trying to pick up 5 valence electrons. So anyway, 4 is about the max. And here are 3 examples of carbon compounds where it's just carbon and hydrogen. So methane is considered to be the simplest organic molecule, 1 atom of carbon and 4 atoms of hydrogen. We can draw out a molecular formula like this, or we could draw it on a piece of paper like this. But another interesting thing about carbon is that it's really a 3-dimensional atom. It's a 3-dimensional element. So when you have an atom of a molecule of methane, it really looks more kind of like this 3-dimensional representation here, where one of these hydrogens is kind of sticking out of the page at you, and 2 of them are going back behind into the page, while the 4th one is kind of just sticking straight up. So it almost looks like a 3-sided or a 4-sided pyramid. With ethane, so that's the second simplest carbon molecule, 2 atoms of carbon, 6 atoms of hydrogen, so that each of those carbons has 4 bonds, including the bond between the 2 carbons. And you can see that it kind of looks like 2 pyramids pointing at each other. And because there is the single bond, what we think happens is at the atomic level, at the molecular level, these 3 hydrogens are spinning in opposite directions because they're free to spin about this single bond here. So imagine like 2 fan blades spinning in opposite directions. Because carbon can form up to 4 bonds, sometimes it may double up a bond. Now, hydrogen can only form 1 covalent bond because it only needs 1 extra electron to form a covalent bond. But carbon, because it has the 4 valence electrons, it can form 2 bonds or 3 bonds with another atom. You don't get 4 bonds with another atom, but you do see 2 or 3. So a double bond, as you can see here with ethylene, that makes the molecule, even though it's just a little bit different in its molecular formula, in its structural formula, and then in the ball and stick model, it is a very different type of compound than ethane because that double bond restricts the rotation. It makes it a very flat molecule. So that's just some of the variation you get with 2 carbon atoms and just filling the rest of those bonds with hydrogen. So when we talk about valency Valency just basically means how many electrons are required to fill the valence shell. Like I said, with hydrogen, it is 1. It can share its electron and borrow another electron or share another electron with another atom, and it's perfectly stable. Oxygen, the valency is 2. It has 6 valence electrons. It can form 2 bonds. Nitrogen has a valence of 3. And as you can see, it's got 5 valence electrons, so it wants 3 to fill that valence shell. And with carbon, your valence is 4 to complete the set of that outermost valence shell with 4 more electrons. So being able to form 4 different bonds really makes it a very versatile molecule versus being able to connect to 3 other things or 2 other things or just 1 other thing. Here's carbon dioxide. And we'll talk about carbon dioxide a lot when we talk about cellular respiration and photosynthesis. But for now, what you'll see here is that carbon dioxide has it's CO2, has 1 carbon atom, and it has 2 sets of double bonds to 2 different oxygen atoms. And this molecule is very important for a number of reasons. But just to give you an idea of how it is shaped, carbon still has those 4 bonds that it can form. It's just with 2 other atoms. And like I said, we'll talk a lot more about carbon dioxide in detail later on. Okay, so we can get a lot of different carbon atoms, carbon molecules, just using 2 types of elements, just using carbon and hydrogen. So most carbon molecules have what we call a carbon skeleton, or a bunch of carbon atoms that are bonded together. And then we can kind of vary the shape or vary the placement of other carbons, other atoms around that skeleton. But just the skeleton itself can vary in length. It can vary in shape. So it can vary in length. For example, here's ethane again. We can add just 1 more carbon and get propane. We can add another carbon and get butane and pentane and hexane and on and on and on. So we can just make the carbon skeleton a little bit longer. We can change the position of double bonds. So here we have a double bond between the first and second carbon. This molecule is called 1-butene. Or we can put it between carbons 2 and 3, and we get 2-butene. And these 2 molecules will behave very differently. Here is butane, 4 carbons, and the rest of the bonds filled in with hydrogens. We can maybe take one of those carbons off the end and then swap it out for one of these hydrogens. And we get isobutane, or 2-methylpropane. But if we do some accounting, if you count up, you'll see that there's 1, 2, 3, 4 carbons, and 4, that's 8, 9, 10 hydrogens. What's this molecule like? 1, 2, 3, 4 carbons. Okay, that's the same. 1, 2, 3 hydrogens, 4, 5, 6 hydrogens, 7, 8, 9, 10 hydrogens. So if we write out the molecular structure, or if we write out the molecular formula here, both of those molecules that we looked at are C4H10, but the shapes of them are very different. And just like with any other change that we make into the carbon skeleton, that's going to change the chemistry, or how those molecules behave in chemical reactions. Another thing we can do is, usually when we have at least 6 carbons in a skeleton, they can form a ring. So here you can see a ring of 6 carbons. And this molecule is called cyclohexane because it's a circle and it's got 6 carbons in it. and all the rest of the bonds are filled up with hydrogens. Um, Another interesting thing that carbon can do is you can form what are called these aromatic rings or these benzene rings, which are alternating between single bonds, and this molecule is called benzene. And again, it has very different chemistry than cyclohexane.